So we're going to change tack now. We're going to go to a talk from Professor Alexander Lyubartsev, who comes from Stockholm University, from the Department of Materials and Environmental Chemistry. His background in molecular and statistical biophysics. So in my world, totally not understandable, but I'm forced to work with it, Alex, as well on my side. So the use of sort of computational tools as predictive models is sort of central to many areas of chemical safety and sustainability efforts at the moment, particularly the use of machine learning and advanced artificial intelligence techniques, which I would call a sort of a sleeping giant of possibility, and actually in this area. So I think, and I'm also reminded of a quote from a famous Spanish philosopher, George Santayana, who said, "Those who cannot remember the past are condemned to relive it." And I think using data to model and produce predictions is extremely important in this area. And I think that quote is very relevant here. And it'll come back when Jenny talks later about the availability of digital data for learning processes. So Alex's title is Modeling of Nano and Advanced Materials. So Alex, the floor is yours.
Okay, so thank you for the invitation to give a presentation in this workshop, and I will talk about modeling of nano and advanced material and research, and I am working in this building at Stockholm University. So what is computer modeling? Computer modeling can be thought that it is experiment on a theoretical model that we consider instead of real system. We describe it in mathematical terms, in terms of model. Say we can describe chemical composition, assume structure, and then we use algorithm, that is set of rules, to make operation with the data in this model. And computation can be rather extensive, that it may require the use of supercomputers, like here is Beskov supercomputer at Royal Institute of Technology, which we are using now modeling. And then computation produces results, and results can be different material properties, mechanical, optical, electronic properties, which are interesting from the application point of view, from the functionality of these materials. And okay, why it is interesting for material processing? So how material processing works? In the input, we have some initial components, some chemical compounds, we have certain synthesis conditions, and we have some recipe that we mix substance A with substance B, heat to certain temperature, and produce some material which may have useful properties and functionality. But what's happening undercover on the atomistic and molecular level, that each chemical compound consists of atoms, and now modern material chemists use the whole periodic table to build up materials. Then certain reactions and molecular interactions happens during the processing, and at the end, final structure of material is formed, and this structure provide required functionality for this material or properties of the materials. So modeling gives insight into molecular mechanism on how this molecular transformation works. And it can distinguish physics-based modeling and statistically based modeling when you model materials. That in physics-based modeling, algorithms are physical laws, that if it can be laws of quantum mechanics based on Schrödinger equation, it can be classical mechanics, it can be fluid dynamics. And in physics-based modeling, it can be done without any a priori information or knowledge about the material, because only fundamental physical equations are used. But this kind of modeling requires large computational resources and answer not always immediately. And we also have a statistical base or data-driven modeling. And here algorithms are statistics on the analysis of known input-output relationship. And here we can methods range from more simple QSAR model, this quantitative structure analysis relationship, and we can use neural networks, machine learning algorithms, artificial intelligence, and give predictions on the basis of statistical based model. And trained statistical models can give results or answer fast compared to physical based model. On the other hand, applicability to new materials can be somewhat limited if this model was not trained on this type of materials, and also not having full insight into mechanism. One can ask that machine is learning. This is fine, but I would like to learn also. Anyway, combination of physics-based and statistical-based model can often give good and usable results. And results of modeling can be everything from just visualization of the atomistic and molecular motion and how all the transformation are going during material processing. You can understand molecular mechanisms and molecular interactions which are involved in material transformations. And then if you have models which are well trained and validated, then modeling can replace experiments for extreme conditions, and you can use modeling for not yet synthesized molecules and materials. And in this way, you can screen prospective materials for certain properties, and it is really used both in material design and in drug design, and its principles also can be used in safety assessment. So I can say that modeling reduces this work in material design and in relationship to safety evaluation, risk evaluation, it may reduce the need for experiments with animals. I can just show a couple examples of using of modelings in our material research at the department. So one is modeling of nanoparticle self-assembly. And this is one of the ways of fabrications of nanostructural materials. The idea here is that you have nanoparticles dissolved in solution. Nanoparticles has a well-defined shape, perhaps with some surfactants. And upon changing of condition, for example, evaporation of solvent, this nanoparticle self-assemble and form ordered structures. And in this example, we had iron oxide nanoparticles of cubical shape or with cubic shape with cutted edges. And if shape is close to cubical, this nanoparticle obviously form cubic lattice when they fold. But if you cut shape on a high level, then it was found that they produce rhombohedral structures with another crystal structure. And these structures, for example, they differ by magnetic properties, which can be used in certain applications. This is another example of producing materials with application to carbon dioxide capture. Of course, I don't need to talk about the importance of this problem, but it is also already happening on the industrial scale. Last year, it was evaluated that something like 40 millions of tons of carbon dioxide was captured at existing facilities, mostly power plants. And one of type of solvents which are used in such facilities are zeolites, and these are materials which are composed of these atoms, silica, aluminum, phosphor, oxygen, in different combination, and now the combination is very high. And these materials form microporous structure with three-dimensional pores of the size, sub-nanometer size. So such pores which absorb efficiently carbon dioxide molecules, but let oxygen and nitrogen passing through. So we did also modeling study of absorption of carbon dioxide with such structure, different zeolite structure and pressure and temperatures. And so this data very useful for optimizing of zeolite structure just for the purpose of carbon dioxide absorption. So this example shows that actually the modeling methods in the material design are now rather matured, and you can just take material, perspective material, and model different properties. And our workshop is about safe and sustainable design, and it would be also interesting to be able to model effect of materials on biological organisms. including possible adverse effects. But this is much more challenging problem because living organisms are a much more complex system than materials, or can say they are much more advanced than advanced materials. So it is challenging, but here we can get help from the knowledge already accumulated in system biology and bioinformatics. Particularly, there is a concept of adverse outcome pathways, which are chain of events in biological organism, starting from the initial contact of nanomaterial with biological organism. And the chain of events go through the chain of K-events and leading to certain adverse outcome. So this idea, which was developed in European nanosafety project, Smart Nanotalks, is that we can try to model using molecular modeling methods, molecular initiating events, which are known to lead to certain adverse outcome according to adverse outcome pathway concept. And for example, this is some preliminary results that is a neural network model, which is trained by computational data and experimental data on inflammation potential in mouses upon inhalation of certain nanoparticles, and computational data with data on absorption free energy of small biomolecules to nanomaterial, and also size shape effect. And they showed certain correlations. Predictions are not right now not high uncertainty. This is mainly because only a small amount of nanomaterials were used for training, about 50, 60, but this work is continuing within NanoSolid project, for which will accumulate and treat much more data. So these are some take-home messages that show that molecular modeling can provide very detailed picture of molecular and atomistic motion and dynamics. So it works like atomistically resolved virtual microscope. And this can be used for screening or optimizing of material for certain properties and functionalities, which is already used in material design, and also progress on the way in developing of modeling methods and tools to assess safety or sustainability of new developed materials. Thank you.
Thank you, Alex, and thanks for really illuminating the various areas where computational power in the future will really help us out.